Hello mathematicians, welcome to our first topic for term 3, geometry of the parabola. So the first aspect of this that we look at is a 2-unit topic called locus. And what a locus is a description of a set of points that obey a certain condition. Or it's the pathway that a single point p of xy follows as it carries out that condition. So for example, the set of all points which are equidistant from a fixed point describes a circle. So we know that already. So if we have a fixed point, then all the positions that we could put another point in, which are equidistant from that, give us a circle of a certain radius. So that locus can be described in words, as we just did, with a picture or a sketch, as we can see opposite, or it can be explained by an algebraic equation. So we know that the algebraic equation for a circle centre AB radius r is this. And the process of describing the locus algebraically like this can sometimes be a simple interpretation. So we read it, we know it's a circle, we write down the formula. Or it may involve translating the word description of the conditions into an algebraic expression. And often we use the distance formula from coordinate geometry to be able to do this. So let's have a look at this example here, where we want the locus of a point that moves so that its distance from the x-axis is always twice its distance from the y-axis. What we'll do is always draw a sketch with a general point, p of xy, placed essentially anywhere on the coordinate plane. We're not trying to do a detailed sketch. And our formal algebraic work should begin. Let p of xy be any point on the plane. The condition for p to lie on the locus is, and then we proceed. Now I'll do a cut down version of that because, as you know, I'm lazy. So I'll just say for p to lie on the locus, and then we'll look at it from there. Now this is a pretty straightforward question. So I've started off for p to lie on the locus. I've done my sketch. I've placed p somewhere. Not sure why, but I often do it in the positive quadrant unless there's a reason not to. And so if I place the point p of xy, obviously it lines up with the point x0 on the x-axis and 0y on the y-axis. So what's our condition? P has to be able to move so that its distance from the x-axis is always twice its distance from the y-axis. So this is its distance from the x-axis, and that is y. And this is its distance from the y-axis, and that is x. And we want the distance from the y-axis, y, to always equal twice its distance to the x-axis. So this is it. This is the locus, y equals 2x. So that's the algebraic description of the locus. The word description up here, I guess, is just this bit. But we can also say, well, this constitutes a line which passes through the origin and has a slope of 2. So any value of p which satisfies this condition is going to lie somewhere on that line. So let's look at our next example. A point moves so that it's always equidistant from these 2 points, and we want to find the equation of its path or locus. So our first task is to draw a graph, draw a sketch. So here we have our axes, and we want 2 points, -1, 6, so here, so obviously not to scale. B at 3, 2, so here somewhere. I put my general point P onto here and indicate my condition, which is that it's equidistant from A and B. So these two distances have to be equal. So for P to lie on the locus, what do I need? I need, as we said, PA to equal PB. But the thing about distance is that when we use the distance formula, it's probably best to square the distance formula. to avoid the complication of square roots. So when we go to our distance formula here, what we're going to find is that if we write down as if we have squared it, we'll get that PA is x minus 1 all squared plus y minus 6 all squared equaling x minus 3 all squared plus x minus 2 all squared. So just as if we'd squared both sides. Next, obviously, we expand this. We'll then gather like terms and simplify. So what we can see is that the locus is a straight line, and that straight line, if we think about it, has to be the perpendicular bisector of the line joining A and B. So if we found the midpoint of A and B, and we found the slope of the line AB, then we're talking about the line which is perpendicular to that. So P has to lie somewhere along this perpendicular bisector. Now our next two questions, well technically locus questions, we've handled before. So the first one, what's the equation of a circle with this centre and this radius? Then we know, unless it says somehow to prove the locus, we just write it down. So that becomes x minus 3 all squared plus y plus 2 all squared equals 16. Find the centre and radius of a circle with this equation. Well, we've done these before as well, where what we do is complete the square. So if we take this expression, just shuffle things around a little bit, so we've got our x squared minus 2x and our y squared plus 6y. And let's take our constants, which are just the 1 here, and we'll shuffle it across to the other side of the equal sign. So what have I got to do to complete this square? Halve the coefficient and square it, which gives me the perfect square x minus 1. And likewise here, I've got to halve the coefficient and square it, which gives me the perfect square y plus 3. What have I done? I've added 10 to the left-hand side, so I need to add 10 to the right-hand side, which gives me 9. So what we can see then is that we're talking about a circle centre 1, minus 3, and radius 3. So we just need to remember what we have known for quite a while, which is that if we have a point which is always a constant distance from a fixed point, we're talking about the locus of that point being a circle. A circle centre at 0, 0 and radius r has this equation, and AB and radius r has this equation. Let's think about our next one. We've got a point moving so that it's always at a distance of 5 units from this point. Now we know that that's a circle, and we actually can write down its formula straight up. So that would be x plus 1 squared plus y plus 2 squared equals 25. But in this question it said, by consideration of the distance formula, derive the locus. So what we have to do is again start with a sketch. So we've got our point -1, -2 down here somewhere. And we want P xy to always be 5 units. We want that distance there to be 5 units. So what's the locus of P such that this condition is satisfied? So P must lie on the locus required if, so it's the distance from P to this point, which is going to be the x plus 1 squared plus y plus 2 squared. So that's what the distance formula says. That has to equal 5. If we square both sides, then what we've got is, as we expected, the equation of a circle, centre -1, -2, radius 5. So now, tackle these Locus questions, but before you do, remember the concept of doing homework with a purpose. Flip back through here and write down 2 or 3 things that you must commit to memory if you're going to be able to do these questions successfully, and things that will need to be in your memory from this point forward.